Good afternoon, everyone. It's my pleasure to be able to share our research with you today on some practical techniques that we've developed for constructing miss ratio curves, or MRCs. This is joint work done with my colleagues at CloudPhysics. Several of the ideas in this talk have actually already been deployed in production as part of a CloudPhysics service that performs caching analytics for workloads in virtualized environments. But this is the first time that we're talking about any of the details publicly. Why is this an interesting topic? Well, the use of caching to accelerate data access is simply pervasive in all modern storage systems. It's well known that performance of caches is highly nonlinear and also varies enormously by workload. So our primary motivation for conducting this research is to make dynamic online cache management practical. This includes making good cache allocation and partitioning decisions to support goals such as improving performance, better isolation, and enforcing quality of service policies. Unfortunately, conventional modeling approaches are generally performed offline. They're simply too expensive to be practical for most online applications. This is especially true for large caches, such as multi-terabyte flash caches, which have become increasingly popular. So let's take a look at what such modeling involves. The plot on the left is an example of a miss ratio curve, or MRC for short. An MRC plots cache size along the x-axis and miss ratio, that is, the fraction of cache accesses that are misses, on the y-axis. MRC shapes vary enormously by workload. This particular MRC reveals a staircase pattern representing various needs in the working set. You get a large win from the first couple of gigabytes of cache, then there's a relatively flat region for the next 8 gigabytes or so, and then another drop off and so on. Note that this is exactly the kind of information that we need to allocate cache space to workloads efficiently. Ideally, we want to know the marginal utility of an additional cache block for each workload so that we can optimize and get the biggest bang for the buck. And an MRC conveniently provides the entire curve, enabling such optimizations. MRC construction typically involves computing histograms of what are called reuse distances. The reuse distance for an access to a block B is defined as the number of other unique blocks referenced since the previous access to B. Reuse distance is sometimes called stack distance because it also represents the distance from the top of an LRU ordered stack of references. To place our work in context, I'll use this timeline to highlight some key events in the 45-year-old history of MRC Algorithm Research, but please see our paper for a more comprehensive treatment of related work. Before the 1970s, cache modeling required running a separate experiment for each and every cache size. In 1970, Matson's seminal paper introduced a single-pass algorithm that computes the whole curve in one shot for stack algorithms such as LRU. Unfortunately, the cost was still high. Order m space, where m is the number of unique references in the trace, and order n times m time, where n is the total number of references in the trace. Research in the 70s and 80s tended to focus on data structure improvements for exact offline analysis. Bennett and Kruskal constructed a balanced tree over all the references to achieve time complexity of n log n. Olkin improved upon this by constructing that tree over only unique references, achieving a time complexity of order n log m. In the 90s through the 2000s, approximate techniques were introduced to speed up offline analysis. Kessler with set sampling and Bryan and Conte with temporal cluster sampling. Starting in the mid-2000s, online techniques were proposed, using new hardware such as UMON DSS for modeling set-associative processor caches, and using coarse on and off sampling periods to reduce overhead, such as in rapid MRC. Later, the PARTA algorithm achieved speedups leveraging multi-core parallelism. And finally, there's been a recent resurgence of interest in this topic that I find very exciting. Over just the past few months, there have been several concurrent efforts using very different approaches. The counterstacks approximation algorithm from OSDI 14 improved space complexity significantly to order log m using probabilistic counters. The rounder algorithm published in SOCC 14 reduced CPU overhead via grouping, and our own work on SHARDS, as we'll see today, approximates MRCs in constant space and linear time. So the problem's very old, but solutions are only now just becoming practical for scalable online cache modeling. Given this context, let's now look at our work on shards. Our original idea was very simple. Place a filter that samples a small subset of blocks in front of an existing MRC algorithm and run the full algorithm over these samples. The key question was whether or not this would be sufficiently cheap and accurate to be practical. Our answer to this question is SHARDS. SHARDS is an acronym for Spatially Hashed Approximate Reuse Distance Sampling, a bit of a mouthful. The word shard by itself means a small part of a whole, and our use of the term is also weakly related to sharding for database partitioning. SHARDS is an approximation algorithm based on randomized spatial sampling. We use deterministic hashing to ensure that all references to the same block are sampled, a very important property needed to capture reuse distances. As we'll see through the results of quantitative experiments, SHARDS constructs accurate MRCs efficiently in a tiny footprint. It's the first constant space algorithm for MRCs. Let's dive in and now take a look at how SHARDS works in a bit more detail. With hash-based spatial sampling, we use a hash function to take a reference to a location L, such as a logical block number, and map it to a hash value T sub I that's uniformly distributed over the range 0 to P, depicted here roughly as painting each location with a random color. Now let's look at the hash value space. A threshold T is used to effectively create two partitions, or shards, one of which is sampled and the other of which is ignored. The sampling rate R is simply the fraction of the hash value space that's sampled, or T over P. In practice, typical sampling rates are significantly lower than 1%. Note that the threshold T can be adjusted downwards to reduce the sampling rate dynamically. When this is done, a subset inclusion property is maintained automatically and guarantees that we won't miss any reuses, since we're just narrowing the sample set. In other words, if we sample a location after lowering the rate R, then we must also have been sampling it beforehand. Finally, we can use a simple check against the current threshold to implement a sampling filter. For basic shards, we simply take this spatial sampling filter and place it in front of an existing reuse distance algorithm, effectively scaling down its inputs. We then take the reuse distances that are output by the algorithm and scale them back up based upon the sampling rate, since each sample represents 1 over R locations in a statistical sense. In practice, each sample typically represents hundreds or thousands of locations. Although this basic approach can reduce the time and space required to generate MRCs by orders of magnitude, it's still a bit unsatisfying in two ways. First, the required space grows slowly, but it's not bounded, making it hard to use in very memory-constrained environments. Second, choosing an appropriate sampling rate can be challenging. The accuracy versus overhead trade-off is hard to evaluate, especially in online systems. This motivated the development of fixed-size shards that operates in constant space. The basic idea is that instead of specifying a sampling rate R, we instead specify a maximum number of samples to track. Placing a hard bound on the size of the sample set results in a constant space algorithm. The basic spatial filtering step operates exactly the same as we saw before. But now, if adding a new sample would exceed the space bound, then we need to evict some existing sample to make room for it. We remove the one with the maximum hash value, shown as T sub max in the figure, closest to T. We then lower the global threshold T to the value we just removed from the set, because we know that any larger values can't fit. Since the rate R is proportional to T, it's also reduced. Now let's take a look at shards in action. The graph on the left plots several example miss ratio curves from applying shards to a real-world storage trace with various sample set sizes. The exact unsampled curve is shown in black. The results are quite good. Approximate MRCs have negligible error for 2K or more samples, and even 128 samples is enough to capture the overall shape correctly. Here, shards is operating in constant space and needs less than 2 megabytes of memory to construct any of these curves. There's no need to determine an appropriate sampling rate because it adapts automatically. I also want to mention that these runs include a simple sampling bias adjustment that we refer to as SHARDS 80J in the paper. Since we now consider this to be part of the core algorithm, all of the results I'll present in today's talk include this adjustment, and please refer to the paper for details. So we talked about how samples get evicted from the sample set to maintain constant space. Let's look at that in a bit more detail. The plot on the left shows how the dynamic sampling rate adapts as a function of reference count for 4 diverse traces. On the y-axis, the sampling rate R starts with a high initial value of 0.1, which is large enough to achieve good results on virtually any workload. As the number of references increases along the x-axis, more unique blocks are encountered and R is lowered progressively. But note that the shape is very different for each of these traces. As the rate is reduced, samples are evicted to bound the size of the sample set, so we need to rescale the weight of older samples. Essentially, an earlier sample taken at a higher sampling rate is worth less than one taken later at a lower rate. We perform a rescaling operation cheaply and incrementally. Again, please see the paper for details. Let's now take a look at our experimental evaluation of shards. We've collected many traces for virtual disks using our SAS-based caching analytics service. As indicated by the figure, block traces are collected locally from customer hosts and streamed up to the CloudPhysics backend for analysis. We evaluate shards with a total of 124 real-world block I/O traces. 106 of these are from VMware virtual disks in production customer environments. These include a mix of Windows and Linux VMs with virtual disk sizes ranging from about 8 gigabytes to 34 terabytes. We also include 18 traces from the public SNIA IATA repository, including Microsoft Enterprise Server traces that include blended IOs from multiple workloads. For our configuration, we used a simple LRU caching policy with a 16 kilobyte block size. So let's look at a few additional results. This array of plots presents some qualitative evidence of shards accuracy. These MRCs model a dozen different traces, some containing more than 100 million references. In contrast to the relatively large trace sizes, shards is configured with only 8K samples and runs in a tiny 1 megabyte footprint. If you look closely, you'll see that there are indeed 2 curves for each MRC, a dashed black one for the exact MRC and shards shown in red, but they're mostly on top of each other. An even larger set of plots appears in the paper. Note that the MRC at the bottom right exhibits the highest error over our full set of 124 traces, and even this worst case still looks pretty good. Next, let's look at a more quantitative analysis of shards error. The graph on the left contains standard box plots for different sample sizes in powers of 2 from 256 up to 32K. A single box plot, one of those vertical slices along the x-axis, corresponds to a given sample size and shows the entire distribution of errors for all 124 traces. The y-axis is in units of the error metric, mean absolute error, or MAE, which has also been used to quantify error in related work. It measures the distance between the exact miss ratio and the approximate one, averaged over all cache sizes. The top of each box marks the 75th percentile of the distribution, the bottom is the 25th percentile, and the black bar in between shows the median. Outliers are represented by dots. Looking at the overall shape, we see that, as expected, with more samples, there's less error. Like many other statistical sampling techniques, we found that shards error is inversely proportional to the square root of the number of samples. In fact, regression analysis yielded a high correlation coefficient of 0.98. This suggests that the error is well behaved, so even if we don't have a hard bound, we could still compute confidence intervals and such. Let's focus for a moment on the box plot for 8K samples. That's the third one from the right. Its median MAE is 0.0027 with a worst case of 0.017, both quite small. But even more interesting is the error rate for tiny sample sizes, which is surprisingly low. It's so good that I originally thought it was a bug, and I still find it rather surprising. For example, with only 256 samples, 75% of the errors are less than 0.02, although there are many outliers. Why does this technique work so well? Our intuition is that most workloads consist of a small number of underlying statistical processes, which operate fairly uniformly over large amounts of data. So a small number of samples is sufficient to model these main underlying processes, and more are needed to capture their relative weights. Now let's shift from examining accuracy to looking at performance. The graph on the left measures the total memory footprint for MRC construction, including code, data, stack, everything. Memory usage appears on the y-axis. Note the use of a log scale. The x-axis shows all 124 traces ordered by the baseline memory consumption in red. Our experimental results are from 3 different implementations. The baseline, in red, is the open source implementation of sequential parta using a standard hash table unbalanced tree approach. For basic shards, shown in green and blue for 2 different sampling rates, we modify the parta code to add hash-based spatial filtering. Not including public domain hash function libraries, this required less than 50 lines of code. As expected for larger traces, memory usage is scaled down by the sampling rate R. You can see this pretty clearly for the leftmost points on the green and blue curves, which are almost exactly 100 times and 1,000 times smaller than the point in red. And you know you're doing pretty well when there's such a large gap on a log scale. For fixed-size shards, we wrote a new implementation from scratch, optimized for space efficiency. Please see the paper for details. As expected, the memory usage in purple remains a constant 1 megabyte. Note that that's more than 10,000 times smaller than the baseline for large traces. We have a similar plot for processing time. This graph measures the total CPU usage required for MRC construction. CPU usage appears on the y-axis. Note again the use of a log scale. The x-axis again shows all 124 traces, this time ordered by their baseline CPU consumption in red. For basic shards with a sampling rate of 0.001 in blue, we see speedups of about 40x to 1,000x. For small traces, note that fixed overheads limit the speedup to less than that would be naively implied by R. For fixed size shards with 8K samples shown in purple, it's a little bit slower than basic shards due to the extra overhead for evictions and managing the sampling set. Nevertheless, it still achieves speedups of up to 200x over the baseline. Overall, shards is several orders of magnitude cheaper than the exact baseline approach. Since the counterstacks approximation algorithm that I mentioned earlier has the best performance of all prior techniques, let's compare it with shards more closely. Actually, counterstacks and shards were developed concurrently. We first learned about counterstacks when their paper was first published after our submission to FAST. For a quantitative comparison, we used the same large Microsoft trace from the counterstacks evaluation with the same exact configuration, in this case a 4 kilobyte block size and only including read IOs. On this trace, counterstacks requires 80 megabytes of memory to achieve a throughput of 2.3 million references per second and an MAE of 0.0025. For a comparable MAE of 0.0026, shards requires 32K samples but needs only 2 megabytes of memory and achieves a throughput of almost 17 million references per second. And if you can live with a little bit more error, still well below 0.01, you can use our default value of 8K samples to use even less memory and achieve an even higher throughput. So overall, on the same trace, counterstacks is roughly 7 times slower and 40 to 62 times bigger than shards. More qualitatively, one advantage of counterstacks is that it supports splicing and merging of MRCs using checkpoint, which is a very nice capability. We're looking into adding similar features to shards. An advantage of shards is that it maintains the identity of individual blocks, enabling it to generalize to non-LRU policies. Let's take a look at this generalization in a bit more detail. Many sophisticated caching policies have appeared in the literature, including FAST, that outperform LRU in many cases, such as ARC, LRS, CAR, and ClockPro. But these are adaptive policies and they're not stack algorithms, so there's no known single pass method like Matson's to speed up their analysis. Our solution is to use simulation, as in the old pre-Matson days. But our simulation is scaled down in 2 dimensions. First, we sample the input references using spatial hashing, say by a factor of 1,000, and then we scale down the simulated cache size, again by the same factor of 1,000. Now, it's not at all clear that this should work, but our initial results are extremely encouraging. Let's take a look at a couple of examples. Here we're using simulators that leverage existing open source implementations of ARC and ClockPro. On the left, we see an MRC for the MSR web trace using the ARC algorithm, and we're plotting results of 64 simulations for each curve. On the right, we see an MRC for customer trace TO4 using ClockPro for 100 simulated sizes. In each case, the exact curve is shown in black, the 0.01 sampling rate in red, and a 0.001 in blue. As with shards, the approximate and exact curves are nearly indistinguishable. The MAE is well below 0.01 in all cases. Also note the interesting non-monotonic bumps, which are presumably due to the adaptive replacement policy behavior occasionally going a bit wrong, and our technique captures this effect faithfully. Overall, we see a huge speed up in memory reduction from scaled down sampling. Exact runs often took multiple CPU hours per point, but just a few seconds with a 0.001 sampling rate. Additional speedup could be achieved by running multiple scaled down simulations concurrently for different cache sizes. In conclusion, we've presented SHARDS, a new algorithm for computing approximate MRCs in constant space and linear time. SHARDS is so efficient that it's practical for online MRC generation. And for the very first time, it's even practical for extremely memory-constrained systems, such as storage controller firmware. It's lightweight enough that you could spin up multiple instances to run concurrently to evaluate the behavior of different caching policies or at different timescales. And finally, we showed that the core spatial hashing technique can be applied to model non-LRU policies, such as ARC and ClockPro, accurately by using scaled-down simulation. Thank you for your attention. I'd be happy to take any questions at this time, and I'd like to invite you to stop by our poster, and if you're interested, our BOF session later this evening. Thank you.
So Jeff Canning, Harvey Mudd College, any chance of getting those other 106 traces?
We can talk about that offline.
Okay. I'm also curious, this is a really cool technique. Have you thought about applying it to anything other than cache analysis?
Yeah, that's a great comment. In fact, it worked so well, it kind of exceeded our expectations that we're looking at other sorts of simulations that may benefit from similar types of spatial sampling. It's sort of a no-brainer for caches because it's inherently spatial, but maybe a mix of spatial and temporal sampling would be equally effective in other domains.
Hi, great work. I had a question on how would you deal with different write policies in caches, such as write back, write through, and so on?
Right, so we talk about this a little bit in the paper. Actually, we've gone through several different implementations of shards to try to model the cache policies used by various vendors. And it's easy enough to do different write policies. We talk about that a little bit in the paper. The other thing that's kind of interesting is because the technique's so inexpensive, you could actually spin up multiple simulations with different write policies and compare them dynamically.
Thank you.
Do you have some ideas, Danny Harnick from IBM Research, any ideas on adversarial traces that will make this go wrong?
I'm sorry, I didn't hear that.
Do you have ideas about adversarial traces that will make it go wrong?
Yes, actually, we've considered that. That's right. If you know the hash function and you're trying to be difficult, you could carefully craft the set of block numbers, block identifiers, to try to force shards to give you a relatively inaccurate MRC. However, there are some simple defenses for that. For example, the hash function we use is murmur hash, and that takes a seed as an input. So, for example, you could randomize the seed before you start it and frustrate most attacks. If you're really paranoid, you could use two different instances of shards with different hash functions and use the one that was better in terms of sampling bias, and I'll refer you to the paper where we talk about sampling bias. In practice, we haven't seen anything like that. It's worked extremely well on all of the traces that we've tried, but you're right that we can't give a hard bound because you could construct such an adversarial trace.
But distribution-wise, is there something that different distributions that will give you worse results? Or?
If you can see from some of the results I presented here and more in the paper, the 124 traces we looked at are very different. Some from FIU, some from Microsoft Research, and a bunch from our own customers running a whole pile of different workloads with very different MRC shapes, very different amounts of locality, and we do well on all of them.
Okay, thanks.